Okay then, so let's begin the subject. We'll start with, I'm not really going to call them definitions, but I assume you know what a point is. And a line can be thought of as a set of points, or we can just think of it as an object in its own right. We shall restrict ourselves to the plane and assume these lines extend indefinitely. Okay, so let's get to some notation then. So then, for points P and Q, we're going to let L equals PQ denote the line joining P and Q. So a fairly natural idea. There's P, there's Q. We're going to assume that there's a line that joins it, and we shall call that PQ. Now, the kind of dual idea of that is that for lines L and M, we're going to let P equals L dot M denotes the point where L and M meet. Okay, so here we have a line L, here we have another line M, and P denotes the meeting point of these two lines. Now, already we're starting to wander away from the intuitive in a sense, because Euclid here would say, well, what happens if lines L and M don't meet? What happens in the case where L and M are parallel? Well, basically, one rather flippant answer would be, well, that doesn't happen because our axioms won't allow it. Because really we're setting up an axiomatic system here. But I haven't told you those axioms yet, so how would we answer this question? Well, Desargues, who tried very hard to push projective geometry forwards much before, he was really much before his time, he was well ahead of his age in developing this. And he said, well, what we can do is imagine that there are some points at infinity. We can kind of augment the Euclidean plane with some points at infinity where these so-called parallel lines can be imagined to meet. And it turns out that that's a very, very nice way of doing it. It sounds very vague, but in fact, one can see, if one looks at the system from 3 dimensions instead of 2, one can see a very, very nice geometric way of making sense of Desargues' intuition. Another kind of intuitive thought to throw in here is, imagine if you look at a pair of railroad lines. Those are parallel, but again, they appear at least to meet off at the horizon, kind of at infinity in inverted commas. Okay then, so for some non-collinear points A, B, and C, we'll say that A, B, C is a triangle. A triangle's special because we could define it by saying about its 3 lines or its 3 points. We'll see more complicated examples later. So that's what a triangle is. Now, we'll refer to these 3 points here as vertices, and the lines connecting these 3 initial points, which we'll call sides of the triangle. And we'll use this convention in general when we're making constructions. Now, this is important because we're going to make a lot of geometric constructions, and so it's nice to have vocabulary that can be used to distinguish between the kind of initial objects that we lay down and the things which are made by subsequently created lines and points. Okay then, now let's get to the heart of the matter. The real heart of projective geometry, I think, at least partially, involves something called the complete quadrilateral. So, a complete quadrangle. My mistake. I should probably just make a note of this up here. So, a quadrangle basically just means a 4 points, a structure created by 4 points, or just 4 points in the projective plane. And a quadrilateral that basically means something which is constructed starting with 4 lines, or just 4 lines in the plane. Okay? So a complete quadrangle is 4 points, P, Q, R, and S, no 3 of which are collinear. Okay, so insisting that no 3 of these points are collinear, it kind of stops these degenerate cases where things are too flattened out to be interesting. So just starting from these 4 points, we can get a fairly rich object with some very important properties. So let's start just by drawing its vertices, its initial 4 points. Those being P, Q, R, and S. Now, how many distinct lines can we get by joining these points? Perhaps you want to pause the video and just see if you can work out how many. The answer is 6. And these lines here, let's draw them in. Okay, so those are our 6 new points drawn in. It's unfortunate that this one ended up way over here, over the top of my writing, but that often happens drawing quadrangles. Anyway, we've just drawn these 6 lines and we'll call those sides. So in addition to these 4 vertices here, these vertices, we also have these 6 sides. So what are they? PQ, PR, PS, QR, QS, and RS. Now, what's very important here, really crucial in fact, is that what we also have here generated by these 3 lines, if I just extend these to annoyances a little bit, we'd see that we have 3 new points generated. One here, one here, and one here. And we call these 3 points the diagonal points of our complete quadrangle. And they play a crucial role in our theory. And it's very interesting that they always come about. So we can label them. Let's call this one A, and this one B, and this one way up here C. So we can use our notation to describe these 3 diagonals. In particular, A is the meet of PS, and QR, B is equal to the meet of QS and PR, and C is equal to the meet of RS and PQ. So these are the diagonals of our complete quadrangle. So I was saying before, the quadrangle, we can just think of it as a kind of 4 points. Some authors refer to them as 4 points because they're essentially described initially by these 4 points here. Maybe I should draw squares around them. There we are. And then everything else, the sides and the diagonals, fall out as a kind of consequence of the positions of the initial points. A complete quadrilateral is 4 lines, let's call them P, Q, R, and S, no 3 of which are concurrent. So, for example, that might be line P. And Q. And R. And S. So this is where we start with these four sides. Now, just as before we had 4 points defining 6 lines, now we have 4 lines defining 6 points, because of the symmetry in our theory, every pair of lines defines a point, okay? So we have that the sides P, Q, R, and S define vertices P dot Q, P dot R, P dot S, Q dot R, Q dot S, R dot S. Okay then, so these 6 vertices, sorry, these 6 extra points, well yes, vertices, they're going to allow us to construct some more lines. In particular, we can draw this line here, between these 2 new vertices, and let's call that one A, and we can draw one between these 2 vertices, B, and one between these 2 vertices. C. So then, in an analogous way to before, these newly generated vertices, these 6 vertices, give rise to 3 diagonal lines. In particular, we have this line here, A, which is the line between P meets S and Q meets R. We also have this line B, which is between Q meets S and P meets R, and this line C, which is joining R meets S and P meets Q. And if you look at the algebra, it's basically analogous to the stuff before. So you can see this duality between the complete quadrangle and the complete quadrilateral ideas.